Hello! Today is lesson 6 of Advanced PCB Layout course. We are going to speak about length matching and we are going to finish our PCB. Let's do it! You already know how to do preliminary length matching of data signals in a DDR3 interface. Now I'm going to show you how you can make this process easier and faster. As an example, we will use this DRAM bank 4. When I order the signals from this bank, from this group, then you can see most of the signals, they are already length matched. Just these two signals, they need to be adjusted. They are shorter. First, what we are going to do, we are going to set up a special rule. Go to Design, Rules, High Speed Match Net Length. Right click, Add New Rule. Double click, name the rule. In this rule, we are going to check if all the signals, length of all the signals in DRAM bank 4 is intolerant 10 mils. Don't forget, you will need to create all these kind of rules for all the data banks, for bank 0, 1, 2, 3, 4, 5, 6, 7. And here then use the correct bank. Press OK. Now watch this here. I cancel this. What just happened? What do you think what this yellow color means? It's very useful. Yellow color means that these two signals, they need to be adjusted. Before, I had to always calculate manually in my head if the length is now intolerance or I need to still adjust the track. Now Altium can make it, and it will use this yellow or sometimes red color to tell you if the signals in this group are in the tolerance of the rule which we just set up. That's not all. Have a look. We can go and use this special feature, Tools Interactive Length Tuning. And based on the rule, Altium will automatically know how long the signal needs to be. So when I click here and I draw the waves, or Altium draw the waves, when there is enough waves, Altium will automatically stop drawing the waves. See? Watch here, this green bar which is here. In the green bar, you can see the exact length of the track. And if the bar is red, it means it is outside of the tolerance. If it's green, it is inside the tolerance. So the length of the track is correct. Okay, I can't film this. What is also very useful, you can adjust these waves. So let's say I would like to make them a little bit smaller, but more waves in whole this line, which is here. I move this a little bit down. A little bit up. Zoom in, clear the mask, and I will make this wider and I will make it a little bit smaller. Wow! Again, really good. Sometimes you need to play with this adjustment because it may do it a little bit different way as you would be expecting, but generally it can be really useful. There are some other things what are useful in this drawing the waves. For example, you can set the space between the waves, and you can also adjust the edges of the waves. I'm going to show you how. You can see now we need to length match only this one signal. So I click here, and let's length match this one. Tools, interactive length tuning. Okay. Press Tab. You can adjust the space between the waves. At this moment, we have 0.3 millimeter. If in our case we use 0.1 millimeter for the track width, then 0.3 millimeter means that the gap, the space between the waves is 3. Ideally, we would like to use 5 times track width. So I will put here what number? 5. Okay. Good. And press number 1. You can make the edges sharper. And press number 2. You can make them smaller or less sharper. Let's say I like this one. Okay. Again, you can adjust the waves by moving these special rectangle around the waves. And when you are happy, you can actually make these to be standard track, because at this moment you cannot work with these waves as a standard track. When I click there, it always draws this rectangle, and you only can work with all these waves. If you would like to work individually with each track, then right click, Unions, Explode Length Tuning. Now when I click there, see, now they are just tracks. We can do exactly same for this one. Now they are just tracks. This will make your preliminary length matching very quick, especially if you have a lot of space. This is very useful feature to speed up your PCB layout. To do length matching for address, command and control signals in Altium, it's not so simple. Why it is not so simple? Because we would need to set up more rules, and we would have to use in these rules values like compare distance between this path and this via and this via and this path, and then also this path, this via, this path. And this is not at the moment directly supported in Altium, because Altium itself cannot really measure what is the distance between a path and via. How do I do it? Or what is the process of the length matching of these kind of signals? I will use my special drawing skills to explain it. This is our address command control signal example. It starts from processor path, it goes somewhere, it splits, then it goes under the memories, it splits again, and then it connects to the top memory, bottom memory, top memory, bottom memory. When I do the length matching of this kind of signal, I do it in 3 steps. In the First step, I focus on these last segments here. I'll switch this off, switch this on. We know all these 4 segments, they need to have exactly same length. So I do something like this. Okay, it's not perfect, but you understand, yeah? Length from this path to this via is exactly same as the length from this via to this path. And it is exactly same as the length from this path to this via and from this via to this path. It's very important. Then I will focus on these segments here. That's the second step. So in the second step, I will make these segments exactly same length or very similar length. Because this was too short, I draw the waves here. After that, our signal will look like this. So it is now balanced signal. Everything what we need to do is we need to adjust the length the way that all the signals in the address command control group have exactly same length from the processor to the memory chip. So everything what we need to do in the third step is to draw enough waves here to length match all the signals within group. Let's have a look how it is done in a real PCB. In reality, when you are doing the length matching of the last segment, then you can do it only under one memory and then just copy and paste it to the other memories. This will speed up your process, it will make it easier. Use mask, click on a net which you would like to length match and measure what is the length of the last segment on the top and on the bottom layer. So it's 202, 181. This one is shorter. Ideally, they should be length matched within 5 mils. So we would like to have this length 202. We need to increase the length by 21 mils. The total length now is 2671. If we add the 21 mils, then the total length after the length matching will be 2692. I'm only calculating this because then I don't have to measure this track all the time. I can just, based on this total length, I can see if the length is correct or I need to adjust the length. Have a look, I'm going to show you. So I draw it here. The total length is 2701, so that's too much. We need to make it shorter because we need 2692. I'm using control key. Do you remember a control key? It then goes through the grid. If I don't use control key, it will start snapping to the snap point. With the control key, I can do it like this. Two, 6, 9, 3. That seems to me correct. So I measure it again. Oops. 202. 202. So it is in the tolerance. Now everything what we have to do when you length match all these signals here all the last segments. Then just click here, copy and paste it, okay? Control C, you already know how to do that. And we just saved a lot of time. Use very similar technique to length match these other segments. Select mask, select the signal which you are going to length match, and then measure it 515. The other one is 478. So we need to, the difference is 37. So the total length need to be 3144. You can also practice your math. I go here and do the length matching. Manually, I will draw it a little bit longer. Three, 1, 4, 2. That's within 5 mils, but I can make it a little bit longer. 3, 1, 4, 5. Good. Now when I measure it, the segments, they should be almost exactly same. 516. This one was 515. Good. Really good. It's a lot of work. It's kind of time consuming, but once you get used to it, it's not so bad. It just looks like it may be difficult. It's not so difficult. Only what is missing is to do length matching for this last segment here, and we will use a special technique to do it. What we will do, we will temporarily remove part of our layout. We will move it away from the board, and we will only leave connection between processor and one memory chip. We will do something like this. Okay, we will temporarily remove this segment, this one, and this one, and only connection what will stay will be from the processor to this memory chip. What we will do then is we will create very similar rule what we created for the data signals, but we will create it for address, command, and control signals. And then we will do the length matching. Be very careful. Only the part of the tracks where you can draw the waves is this one here. So you can draw the waves here to do the length matching for all the signals in this command control address group. Do not draw waves here, do not draw waves here. Why? Because then you break the balance between these segments here. Only draw the waves here. Have a look on a real example. I have pre-selected the tracks, half of the track on the layer 10, so we can move it away. We still need to select also the tracks on layer 1. So press Shift, I add these tracks, and on the layer 12, Shift, add these tracks, Shift, add these tracks. What I don't want to move away are the bias. So I go to PCB filter, use Is track, apply to select it. Now we only have selected the tracks which we don't want to have there for the length matching. I go and copy and paste it. Ctrl C. I remember the point which I use for this and put it here. Okay. We can safely delete these tracks. When we have a look what left, you can see we have only the track on the top layer, then it goes to the middle on the layer 10, and then on the layer 3 it goes under the processor for all the signals. See? From the top on the layer 10 on the layer 3. Now we can very nicely do the length matching and use the standard Altium rules to help us with this. Go to Design, Rules, High Speed Match Net Length, right click, New Rule, double click, name the rule, for example DRAM ADDR control, and what we would like to set. What do you think? All the signals in the net class called address, DRAM address control to be length matched within 10 mils. Press OK. Cancel. I will cancel this. Can you see what we just did? This rule now tells us that all the signals are properly, or almost all the signals are properly length matched, and they have very similar length from the processor to the first memory chip, except this one, because I changed this one to show you that you can also do the length tuning when you set up this rule. So I go on the layer 3, have a look. This is the track which we need to length match. I just go, use the tools, interactive length tuning, and do it. This will help you a lot. See how quickly we were able to length match these address command control signals just by using this simple trick. I'm sure you know how to apply it into your designs. And this kind of technique, moving part of the layout away, you can use on many kind of different topologies or different kind of layouts. Once you are happy with the length matching, then you can put the layout back to your board and disable this rule, because this rule will not apply anymore. Go and enable all the layers, select this. Be sure you are on the bottom layer. Ctrl C. I go, show only one layer, and Ctrl V. See, now almost all the rules, they are broken because the total length has changed. Go to Design, Rules, and this is the rule which we do not need anymore, so I will disable it. Okay. Cancel. One useful tip: if you don't have enough space for these waves which are here, you can move some of them to these segments. It will look like this. Let's say we would like to remove this wave. So I will do it this way, and we are going to put it here, like this way. That's something weird. No? No. If you remove one wave here, you need to create two waves. One here and one here. I'm sure you know why. Because the length between this wire to this wire has to be exactly the same as the length from this wire to this wire. So if we take the length from here and put it on this segment, we have to put it also on this other segment. Sometimes there is space around these tracks, so you can do this. But always consider if it's better to put the waves here or here. Now let's speak about the length matching the other interfaces, LVDS, HDMI, Ethernet, and these kind of interfaces. How do you know what are the length matching requirements for them? You can read it in design guide. Sometimes. Not every design guide will describe the length matching requirements for LVDS, for HDMI, and these kind of interfaces. What you are going to do then? You can, for example, go on internet and try to find something similar, or a design guide which will describe the length matching requirements which you need to know. Or the easier, simpler, faster way to do it is just length match these interfaces within 10 mils. I read a lot of design guides and I know the rules for length matching these interfaces like LVDS, HDMI, and these signals are not so strict. But when you length match these interfaces within 10 mils, you will know the length matching is correct. And also, once you are doing the length matching, then even if the requirements are length matched to 100 mils, 50 mils, once you are doing it, once you are drawing the tracks, it is not a problem to do the length matching within 10 mils. So just do it. And then you don't need to think about this. For example, have a look on the module. LVDS interface, here are the high-speed signals, LVDS signals. You see, almost exactly same length. HDMI, almost exactly same length. Ethernet, almost exactly same length. There are some exceptions. For example, PCI Express. On the internet, I found this layout checklist for this Intel Ethernet chip, and I would like to show you the PCI Express requirements. You may be surprised, the requirements for the length matching of PCI Express are not so strict. Here it is. Match trace lengths between PCI Express pairs within 3 inches. It means the RX and TX signals of PCI Express, there can be difference between them up to 3 inches. It is quite long. 3 inches is quite long. So, for example, if both chips are on your board, like processor or chipset connected to Ethernet, then you may be quite relaxed if these chips are connected through PCI Express. You don't really need to do length matching for these PCI Express signals. Usually difference will fit between these 3 inches. If you are connecting this PCI Express to the slot, then you may want to consider somehow make them approximately same length. Again, what I wanted to say with this, if you are not sure how to length match a particular interface, then most of the time it is correct just make the signals in the interface exactly same length and it will work. What to do with the slow buses, parallel buses? How to length match these signals? I use this kind of recommendations here. This is the ComExpress design guide, you already know this. Find the PCI routing recommendations or IDE routing recommendations, and they say like say PCI transfer rate 33 megahertz, length match the signals within 200 mils. Or here on the IDE you can see length match the data signals within 200 mils, then length match the read and write signals within 100 mils, but these read and write strobe signals, they need to be also in the relationship with the data signals, and these two signals, they cannot be longer than 450 mils comparing to the data signals. This means that when you are routing slower interfaces, for example SPI, SD card, MMC, ID, and all these other buses, you can be more relaxed. You can use tolerance 200 mils. Again, what I said before, once you are doing the length matching, you will do nothing wrong if the signals are a length match within 10 mils. But in these slow interfaces, it is not so crucial. And if there is no space on your board, for example, then do not hardly try to route them within 10 mils. You can be a little bit more relaxed. Few words about the preliminary length matching. Do the preliminary length matching on most of the signals after you connect everything, because when you connect everything you will see where is space, you see where you can move the tracks, other tracks, to create space for the waves. Do not spend too much time doing the waves. At this stage only draw the lines a little bit longer than it is required. By the end of the design we will do the fine-tuning, we will make them nice and we will make them exactly the length as it should be. I normally use two kinds of techniques. Do preliminary length matching. Normally I start with this signal which is further from the core, which is drawing the envelope, the edge of the envelope of the area of the signals which need to be length matched. I will make this, I normally make this signal as long as possible. I draw it in the area where it is possible without any waves. So it will be the longest signal from whole group. Then I continue with the second signal, this one, second signal from the outer layer. I draw it close to this signal, which I did, and if it's needed, if this signal is shorter, usually it is shorter, I add a wave to make it a little bit longer than this signal here. Again, continue with the third signal, route it close to the second signal. If needed, add two waves to make it a little bit longer than this signal. Then this one and this one, and continue also with this. if I go and if I draw this last signal which is here, and if there is no space to achieve the required length, then I use some kind of second technique for the length matching, and I go from the shortest track and make it longer, as long as it is possible to make it in the layout. Once I make it longer, then I go find again the shortest signal, make it longer. Shortest signal, make it longer. Shortest signal, make it longer. This technique usually helps me to achieve the length matching which I need. Don't forget, when I say length match an interface within 10 mils, I mean the difference between the shortest signal and the longest signal in the interface should be within 10 mils. But if we are speaking about length matching within differential pair, so between plus and minus signal of one differential pair, these always need to be a length match within 5 mils. It's important, okay? So whole interface within 10 mils, but differential pairs within 5 mils. If you are not sure what kind of length matching rules you should use these two numbers. Couple of tips for length matching, and this one is really interesting one. Have a look. Sometimes it is important how many waves you draw and where exactly you place vias. Let's measure what is the length of this track here. It is 6 to 8. What do you think? If we measure this one here, what the length will be like? It will be exactly same. 6 to 8. Now, watch. I will do something. What if we do it this way? Will the tracks will be still exactly same? What do you think? Let's measure it. 5, 1, 2. 5, 4, 5. Big difference. Why there is the big difference? Because here are 3 small waves and 2 big waves. Here are 3 big waves and only 2 small waves. So it depends how many waves I will draw. If you draw it only like here, so 2 small waves and 2 big waves, you will see the tracks will be exactly same. Let's measure it. 4 to 8. 4 to 8. Okay? So sometimes you really may need to be aware how many waves you are drawing and how exactly you place the vias, because it can cause big difference between the length of the plus and minus signal in differential pair. Here is another very interesting example. I would like to show you how big difference it is between the situation when you use full waves comparing to small waves. What do you think? Which of these tracks is longer? This one with 1 full wave or this one with 3 small waves? I'm going to show you. These 2 tracks which are here, they are exactly same. 370, 370. Now I measure this one here. It is 388. And now I measure this one, which is here, and it will be, what do you think, longer or shorter? 385. So it's shorter. Even here are 3 waves, this track is shorter than this one here. And what makes the difference, what makes big difference when you are doing length matching are these parts here. That's why I call this full wave. Full wave will have this corner, this part, this corner, this part, corner, part, corner. Comparing to these simple waves, they have only corner and this part, corner, this part. Okay, so if you need to do length matching and if you need to add a lot of length, always prefer to do this kind of full waves instead of doing just these simple waves. Same here. What do you think? Which one is longer? This one or this one? Let's have a look. 328. Three, 4, 3. So this one is much longer comparing to this one. Again, simple wave, full wave. In space, what they take, it's approximately exactly same. But with these full waves, you can add much more length. This is a good one. What do you think? Which one is longer? This one, which is here, or this one, which is here? 156. And is it going to be longer than 156 or shorter? 183. This signal is much longer than this signal here. This technique, which is used here, going behind the wire and then coming back, adds a lot of length. So in case you need to add a lot of length to your tracks, you may want to consider something like this. Okay, go behind the wire and then back. Be careful, do not create some big loops or something like that, but as you can see it here, you can safely use it in your designs. This is a very similar example. If you have a track on layer 1, which is connected on layer 2 with 2 microwires, and then it continues on layer 3, then in the case, if you need to add length to this kind of track, you can very simply just use this trick. Instead of placing the microwires this way, you can place them this way. Now when we measure the difference between this one, which is 192, and this one, which is 223, you can very nicely see this one here is much longer comparing to this one. Just by using the simple trick, placing the microwires this way instead of this way. And one more tip from memory length matching. Always be sure you leave enough space for the clocks, because the clocks are usually the longest signals from the memory interface, and you will need a lot of waves to length match the clocks. Very often I do the waves of the clock on top or bottom layer, because usually I do not draw any other signals on these layers, so there is a lot of space, as you can see here, for example. Now I would like to speak about memory interfaces. There are some other interfaces, like PCI Express, HDMI, LVDS. All these, they are high-speed interfaces, but they are not so difficult to route. These are differential pairs, and everything basically what you need to know is the proper way of routing differential pairs. For the memory interfaces, that is completely different story. There are a lot of different situations in the layout for memories, and I would like to mention some of them. For everyone who is routing memory interface, it's very important to know difference between T-branch and flyby topology. Here on these two pictures you can see memory modules, standard memory modules which are used in computers. This one is DDR2 memory module, this one is DDR3 memory module. And you can see they are routed different way. This DDR2 memory module, which is here, it is using T-branch topology. How do you know? Because we were speaking about it. You can very nicely see these signals, they go between the memories and then they split. They go here and here. Again, between memories, here are the memories located. So they go between the memories and they split again. And here they go under the memories. Here is one memory on top, another on the bottom, and here they split again. So this is balanced T-branch topology. This one here, this is DDR3 memory module, and it is using flyby topology. The difference is that all the signals here, they go to this memory chip, the first memory chips. They are two, one on the top, one on the bottom, and then they all go to the second memory chips. Then they go all to the third memory chips, 4 memory chips, and termination resistors. It's very important to know when to use T-branch and when flyby topology. It is very important because schematic for these two, it is almost exactly same. If you think about it, these pins, they are connected to all these memories which are here. It's exactly same here. Schematic for this and this is almost same. These pins which are here are also connected to all these memory chips, but they are routed different way. It's important how you draw these tracks. Usually you will need to route DDR2 memories with T-branch topology and DDR3 memories with flyby topology. Sometimes there are exceptions for DDR3 memories, and they can be routed also with T-branch topology, as you can see, for example, on the IMX6-REX module. IMX6-REX module, it is DDR3 interface, but it is routed by T-branch topology. Always read design guide, they will tell you what you need to use for the memory interface routing, if it's T-branch or flyby. Sometimes you can use both, you can choose which one you would like to use. If you would like to see the memory layout, you can go to this JEDEC website and you can download it from here. It's free, you just need to register. To see the PCB file, you will need to download also this Allegro free physical viewer and open the files from this website in this free viewer. I highly recommend you, if you are working with memory interface, go here and download some of the examples. It will help you. I do it exactly same way. If I'm not sure, I find the specific module here and I have a look how the professionals did the layout. You already know what is important for the T-branch topology, but what is important for flyby topology? read the design guide. But this is basically what you will find out. I'm going to show you. For the flyby topology, it's important that you route signal from processor or FPGA to the first memory chips in some kind of tolerance. And then when you route to the second memory chips and the third, fourth, and the other memory chips, you need to keep the distance of all these segments exactly same or very similar length. I'm going to show you. This is the Allegro free physical viewer. This is a memory module, and I'm going to zoom in so you can see how I measure it. I need to disappear because otherwise you will not see it. Now I use this measure tool, and I first measure this yellow track from here to here. 4,203 mils. For the blue one, it is 4,052 mils. So it is in some kind of tolerance 200 mils. From this pin to these pins which are here. But have a look now. From this memory chip to these memory chips which is here, the distance is 742, and for the blue one it is 742. See? Exactly same length. So between the memory chips you need to route these tracks, these segments, exactly same or very similar length. Do you know what I just measured? I measured the distance between this path from this memory connector to this path, which is a path of memory chip. If I zoom in, you will see this is layer 1, top layer. This area is under memory chip, top memory chip, and this small circle, this is a path of the memory chip. This big circle is a via, and this is a 4-net. So the yellow is a 4-net, the blue one is a 3-net. So one more time, I measured the distance between this path and this path which is here. Okay, 423, and the blue path which is here, and blue path which is on the top, 4052. And then I also measured the distance between these two memory chips. So I measured what is the distance between yellow path from here to here, that was the 742, and what is the distance between blue path from here to here. That's the distance between these two memories, 742. You see the distance is exactly same. We are looking for this edge distance. This edge distance, it means it's the copper distance. It's the distance of the connection, copper connection between these two paths. So don't forget one more time, for the flyby topology, it is very important that all the signals which are connected to all these memory chips, they need to be routed from the processor or FPGA in some kind of tolerance to this first memory chip. What kind of tolerance? Read in the design guide. If you don't know, use our magic number 10 mils. So if you don't know, route all the signals from the processor to the first memory chips in tolerance 10 mils, and then all the segments which are routed between this memory chip and this memory chip, they need to be exactly same length. Use 5 mil tolerance if it's not specified. Again, between these two memory chips, all these segments which are here, they need to have exactly same length. Tolerance 5 mils. Again here, same here. I'm sure you understand. Connecting the data lines in flyby topology is exactly same as connecting data lines in the branch topology. It is just direct connection from the processor or FPGA to the memory chip. On this module, there are a couple of very interesting things what I would like to speak about. For example, they break one of the rules what you learned. Do you know which one it is? They do not route all the signals from same group exactly same way. Have a look. These two signals, yellow and blue, are from same group because it is A4 and A3 signal. And here, when they change the layer, then the blue signal continues on the signal layer 3 and yellow signal continues on signal layer 4. So they are not routed exactly same way. You can use this if you know what you are doing. You can use this if you have 3 layers available for address command and control signal routing, because you need one layer to go up and then you need 2 layers to connect the memory chips between them in parallel. I sometimes use this technique because it speeds up the layout process and it's quite easy to do. What is the advantage? Do you know what is advantage of this? You can very easily route signals between the memory chips, and you can very simply just copy and paste these parts, these segments which are here. You can copy and paste them here, use for the connection to the other memory chip, and copy and paste it also here. See, here are some waves, here are some waves. It is exactly same here, because these segments here, they are copied and pasted here. Why is it possible? Because if you use 2 layers for these address command control signals, you have enough space to route these signals straight and directly between the chips. Normally, there is no space. See, this is memory chip here, and see how many tracks otherwise need to be routed on one layer only. These connections, they cannot be straight. If you use 2 layers, you can make them nice and straight. But you need to know what you are doing. If you are not sure in high-speed design, use the standard technique. Route all the signals from one group on one layer only. If you know what you are doing, you can route address command and control signals this way. The second interesting thing. Have a look here. How they connected and how they did fan out for address command control signals. See here? Compare with our layout here. Can you see something different? Have a look on these vias which we have here. Have a look what they have here. It looks like they don't use so many vias. See? We have a lot of vias here. They have only few vias here. How is that possible? There is exactly same number of pins, exactly same number of connections, nets. They actually use exactly same number of vias. They just don't place all of them here in the middle. They place some of them also here and here. Can you see them? How is this possible? Because they use something what is called memory mirroring. They connect the top memory chip exactly standard way as also we do it. So A3 signal is connected to A3 pin of the memory chip, A4 is connected to A4, A5 to A5, A6 to A6. If you have a look how the bottom memory chip is connected, you will see something different. A3 signal is connected to A4 pin. A4 signal is connected to A3 pin. Okay, and here are some other signals. What will this swapping do in the layout? Have a look. This is A3. Normally, you need to go from one side of the memory through a via in the middle and to the other side of the memory. Have a look where this A4 is located. It is actually very close to the A3 memory pin, which is on the bottom. So basically, if you can do this swapping, you can place a via here and connect these two pins to this via. That's exactly what they do here. See? Be aware. You need to check if your design supports this kind of memory mirroring. In this example, I only wanted to show you that something like this exists, so you know about it. But if you are considering to use it in your design, you always will need to double check it. Just to make it clear, if you are not sure if your design supports memory mirroring, do not use it. Do not swap the address signals, okay? You need to know what you are doing. If you are not sure, use the standard way, connect the memories standard way. Another interesting thing from this design, which is here. I told you, you can learn a lot from these modules. We are going to speak about how they connected data signals. In our design, in the IMX6 module, the top memory chip is connected to some data lines. The bottom memory chip is connected to different data lines. In this example, they connect the top and the bottom memory chip to the same data signal. And because it is high-speed interface, it is very important how you make the layout for this kind of connection. Let's have a look. This is the top memory chip. You can see this is path of the top memory chip, and it is connected to this via. On the bottom, there is bottom memory chip. This is path of the bottom memory chip, and it is connected to the same via. Then from the via, the signal goes here to the series termination resistor, and then it is connected to processor or FPGA. And it is very important how you connect this last segment of the memory chips. It's very important that you place this via very close to this path, and the distance, the length of this segment is short as possible on the top layer and also on the bottom layer. They need to have exactly same length, and the via need to be placed close to these paths. How is it possible? It is possible because you can do the pin swapping. So basically, if you have this kind of situation, what you need to do is you route the top memory chip, and then you actually assign net to this via, which is here. And then when you will be connecting the bottom memory chip, you already know what is the signal here. Here, initially, you may have different net, different data signal, but you go to the schematic, you do the pin swapping the way that you will have here the net name, the signal, which is in this via, and then you can make the connection. So this is the proper way how you need to route data signals if they are shared between top and the bottom memory chip. Don't forget, place the via very close to the data path, make very short connection, the length has to be exactly same on the top and on the bottom layer, and if it's needed, you need to do pin swapping on one of the memory chips. When you are routing memory interface, it is very important where you place and how you connect termination resistors and capacitors. There are many kind of situations how they are placed and how they are connected. So you always need to read your design guide. You always need to read the datasheet and follow the recommendations for your specific case, for your specific design. It's very important, okay? For example, here in this layout, they place these series termination resistors into the data lines. You can see them here. Here are another termination resistors. They are placed on the end of the signals and connected to termination voltage. In IMX6 Rex module, you can see termination resistor here, which is connected to the clock signal, and it is placed on the end of the clock signal. Don't forget, you always need to know where to place these terminations, resistors and the capacitors. As I say, it is very important. I have a question for you. What do you think? How does this kind of design work? Because it's clear why we designed these memories by T-branch topologies, why we connected these memory chip by T-branch topology. Do you know why? Because we wanted the signal from the processor arrive exactly at the same time to all these memory chips. That's exactly the reason why the distance between the processor pin and this memory pin need to be exactly same as distance between processor pin and this memory pin, and it needs to be exactly same as the distance between processor pin and this memory pin and this memory pin. Okay? When something starts here and the distance to all these memory chips is exactly same, the signal will arrive to all these memory chips at exactly same time. But then, how does it work here? Because if the signal starts here from the processor or FPGA, it arrives to these first memory chips, and a little bit later it will arrive to these other memory chips, and a little bit later it will arrive to these other memory chips, and a little bit later it will arrive to these other memory chips. So the question is, how does it work? Clever people designed this DDR3 interface, and basically what you need to do, you need to introduce delay into these data lines, which will correspond and which will compensate the delay which will be between the time when the signal arrives to these first memory chips, these other memory chips, and this one and this one. So the delay in the data lines will compensate this delay between the memory chips. But now we have another question. How do we know what kind of delay we have to use for the data lines? We will use something what is called DDR3 software read-write leveling. It's very simple, very clever. Have a look. From the source, from the processor, clock and DQS signals, they will start together. You can see here. But when they arrive to a memory chip, they will arrive in different times. Why? Because the distance is different. So what do you think? What will arrive first? DQS signal. Why DQS signal? Because usually data signals are shorter and the address and clock signals, they need to travel around the memory chips. So they need to travel longer way, so they will arrive a little bit later. Here you can see DQS arrives first and then clock a little bit later. In the special mode, the memory chip will put on data lines, on the data bus, the value of the clock at the time when DQS arrives. See, in this time clock was 0, so on the data lines there is 0. Now everything what you need to do is just put a little bit delay to these lines. And you move this DQS a little bit later, and then you read what is the value of the clock. Again, in the software, you put this delay a little bit longer. DQS will arrive a little bit later. It reads the clock value and it will appear on the data lines. You repeat this, repeat, and then once what you will find out is when the 0 will change to 1. Here you can see it. When you put there enough delay, you will find exactly the time when the clock will change to 1. That's the technique what you can use to find what is the delay between the clock and the DQS signal, which you need to use to synchronize them. Why we are speaking about this? Because sometimes when you design DDR3 layout, especially in the cases when the memory chips are soldered down to your board, you need to run DDR3 calibration. During this calibration process, the software will measure the delays and some other values, and then when this calibration will finish, it will provide you with numbers which you need to then set in memory controller. So the software or the firmware which initialize DDR3 interface will take these values and put them into the DDR3 controller registers. It's very important because then if you don't calibrate this kind of interface, it may not work properly. How does it look, this calibration? It's very similar between different platforms. Here is example for Freescale, here is example for Texas Instrument, and I like this example because here you can very nicely see when the individual memory banks will actually some kind of start working. Each number here represents one data bank, and when it is 1, it is not working. When it is 0, it is working. So you can very nicely see when this data bank 0 is not working. Here they change the delay. Not working, and it starts working, yeah? And then it stops working again. Here is data bank 1, again, not working, starts working when the delay is like here. And by the end of the calibrations, here are the values what you will get. So it will tell you, put this value to this register. Put this value to this register. Okay? Usually you put them into U-boot. For Texas Instruments, very similar. Again, it measures some values exactly for each data byte, and then it will give you the numbers which you need to use for specific registers. It's very simple. What is important is do not forget run the calibration if you put down the DDR3 memories on your board. And it's also important to know how it actually works, because it will help you understand the layout better. Now the question is when you need to run the calibration. You need to run calibration for every specific layout. Yeah, if you do some changes in the layout, you need to run calibration. But once you have this layout and you produce board with exactly same components and exactly same layout, you don't have to run calibration for every board. But if you change, for example, memory size, you may need to run the calibration. If you change memory manufacturer, you may need to run calibration, even for exactly same PCB. Don't forget. Always consider if you need to run the calibration again or not, or if you are not sure, just run it and test the board. I said everything important what I wanted to say about the memory interface, and now we can move to different topic. When you finish preliminary length matching, then do something what I call spread the tracks in your design. Many times I see boards, finished boards with tracks routed like this, with a lot of space around the tracks. To improve your layout, don't leave it like this. To improve your layout, reroute the signals and use the free space. Okay, for example, like this. Like this. You see the space between the tracks? And then instead of going very close to this track, go away from the track. You can route it also this way, away from the track. Do exactly same here. You can go here down, make it wider, play with it. Same here, spread the tracks. Why we are doing it? Because then the crosstalk between the tracks is lower than in this case. This is much better layout. If you have the space, do it. Small tip. If during the phase 2 you need to move some tracks or you need to move some wires and you will get a violation, then clear it immediately. For example, if I move this wire and I see here is a violation, during the phase 1 you can safely ignore it. It's not a problem. During the phase 1 in this area you probably will be redrawing these tracks many times. So in the phase 1 it is really enough if you fix this violation by the end of the phase 1. In the phase 2 it is different. In the phase 2 keep your PCB clean from the violation. It is good for your psychic because you will see the PCB is still fully routed. Everything what I need to do is just do this small tweaking. If you don't clear these violations in the phase 2, after a few days your whole PCB may be green again, and then you will see like, oh, there is still a lot of work. So in the phase 2 you do it like this. Okay? Immediately fix it. Go through every layer and redraw the tracks if needed. I'm sure you understand. I redraw also this one. I don't like this. In the phase 2, keep the tracks nice. Okay. When you finish improving your tracks and your layout, then you can move to the next step. And next step is all about polygons and planes. Before you start working with the planes, with the polygons, check if you have set up the pullback of the power planes correctly. Go, press right click and select Layer Stack Manager and have a look if your ground plane pullback is set to 0.1 millimeter. This is also ground plane and it is set to 0.1 millimeter. In the original IMX6 Rex module, you will not find this plane. But because I would like to show you something, I set up this new internal power plane. It is 3.3 volt power plane. And for the 3.3 volt, we need to set the pullback to be deeper than the ground planes. So I set it to 1.1 millimeter. Do you remember what is pullback? Pullback is the distance between the board edge and when the copper of the plane will start. So if it's 0.1, then it is board edge space 0.1 millimeter, and here is the copper. Have a look. This is a layer 4. That's the ground plane. You see it starts 0.1 millimeter from the edge, and this is the power plane. It starts deeper from the edge, 1.1 millimeter. Normally, if you create a power plane layer in the StackUp Manager, then you can go on the layer, double click on the power plane, and you can assign a net to the plane. Sometimes you may want to have more different power planes on this one power plane layer. How to do that? Very simple. Just place line and draw the line around the area which you would like to have different. Then just double click and change the net. For example, this one. See, this one is 3.3, this one is 5 volt. Normally for my designs, if I need to draw different powers on one layer, I use a signal layer. Normally in my designs, all the power planes are just one net. I don't use this. I don't split power planes. Why? I just found it more simple to work with the polygons. Polygons are the power planes which are placed on signal layer. I'm going to show you. So this is a signal layer, and we are going to create a polygon, and we will assign a net to the polygon. Place polygon pure. Here you can select the net, press OK, draw the polygon. This is the copper, field copper. If you need to adjust the shape of the polygon, you can just go and drag the edges. Watch where are these squares. It is very important where are these squares, because if you go on the square and when you drag the mouse, then it will change the shape. If you go here on the edge, you can move it. Okay. If you need to change the shape, for example, in this place here, press Ctrl, hold it down, the square will appear, and you can drag the edge. If you need to delete this square, again go there, move it and delete. These are the simple things what you need to know about drawing and working with the polygons. When you are working with polygons, there are some parameters what I sometimes change during the layout. For example, double click on the polygon and have a look. This I normally do not change, but I sometimes change this. If you draw a very small polygon, smaller than this area, then Altium will not fill it up with copper. In that case, you may want to disable it, or you may want to make this number smaller. Here, this number here, sometimes I need to change it. This number here will cause, if it's too big, it will cause that in places like here, between these vias, copper will not flow, because it actually specifies the smallest track of the polygon. And if this size here is smaller than this number which is here, copper will not flow between the vias. You understand? And what I also normally do here, I set up this pour over all same net objects. If you use this option, which is here, pour over same net polygons only, it will look like this. Even this is polygon for plus 1.5 DDR, and this is track for plus 1.5 DDR. You see, it creates the clearance between the track and the polygon. If you set this, it will flow through the track. See? You see the difference. Normally, when I start working on a design, I go to DXP, Preferences, PCB Editor, Defaults, and I set up default polygon values. I'll leave this as it is. Normally, I'll leave this one. I also leave this one. Here I set the minimum track width. Here I select pour over all same net objects, remove dead copper. Do you know what is remove dead copper? This basically means that if you draw a big polygon and there is an area which is not physically connected to this polygon because there is, for example, too many vias very close to each other, so the copper cannot flow to the area between these vias, then if you check this, it will remove this dead copper which is not connected to the big copper. It will remove it from this area. So I check this, I check export, and this is the proper setting what I normally use. Don't forget, in the case if you need to place a power via very close to the PCB edge, then draw it like this. Okay, do not draw this polygon edge closer, because you need to keep the distance between the ground edge and the polygon edge, you know, based on the 20 edge rule. Only in this area where the via is placed, go with the plane around the via and then go again deeper into the PCB. Yeah, like here. Now I would like to show you something. Normally the gap between these polygons is specified by the edges of the polygons. So if I draw this polygon here and I draw this other polygon here, then the gap between them, see, it's from this edge to this edge. But What if you would like to have this gap wider? What if instead of, let's measure this, instead of 0.2 millimeter, you would like to have this gap around this polygon 0.4 millimeter? You can create a rule. How to do it? First, we will have a look what is the name of this net here. So I double click and it's called plus SATA VP. Now go to Design Rules, Electrical Clearance, right click, Add New Rule. I already created the rule, it's here. In the rule, you need to say that you are setting up the rule for the net plus SATA VP, and it will apply to all the polygons which are around this net. And between this net and these other polygons, we would like to have the gap 0.4 millimeter. Okay. I will cancel this, and we need to rebuild all the polygons. So right click, polygon action, rebuild all. Now, what do you think? What is going to happen? This gap is going to be wider, but how it is going to be done? Because it is wider, it has to cut one of the polygons. You can see now what happened. It cut it out copper from this polygon which is here, and it kept this polygon the size as we draw before. But here I don't like it here. In this situation it cut it off the copper from our polygon and it left this polygon. I would like to rather cut out copper from this polygon and leave this one whole. How to do it? It's simple. There is something what is called Polygon Manager. And in the Polygon Manager you can set priority of each polygon. And if polygon has higher priority, then it means it will draw it first. So everything what we need to set up higher priority for this polygon than its priority of this polygon. So this polygon is filled up first, and then this one is filled up with the copper. What we need to know? We need to know how these polygons are called. So double click and check what is the name of the polygon. I used this name test1 just because then you can remember it better. So this polygon is called test1, this other one is called test2. Now when I right click on a polygon and I go to the polygon manager, here I will find these two polygons. They are here, test1, test2. And you can see priority of test2 is higher than priority of test1. So everything what we need to do is we need to swap them. Okay, now this test1 has higher priority comparing to this one. Press OK, and we will redraw the polygons again. So rebuild all. Now watch what will happen. It takes some time. What do you think? Will it work? Ta-da! See? Our polygon is exactly the size which we specify by these edges, and it cut it off the copper from this other polygon. Great. Sometimes it's useful. Sometimes you really may need to set up the priority of polygons. Now I would like to speak a little bit about thermal relief. Thermal relief specifies how a polygon or how a plane will connect to via or through hole pin. Here you can see example. This is a ground plane and here are ground vias, and you can see they are connected through thermal relief. This thermal relief specifies 4 connections and these 4 gaps around this via, ground via. Normally in my designs I connect all the vias directly to the polygons and planes. How to do it? Go to Design, Rules, Planes, here, Power Plane Connect Style, and select here Direct Connection. You may want to do also exactly same for Polygon Connect Style, Direct Connection. Press OK. Cancel. See? Now the plane goes directly to the vias. This is great. This is really good. But we may need some exceptions. Do you remember from previous lesson? For example, for the through-hole ground pins, we really would like to use a thermal relief because it may be really hard to solder them down. So we need to set up a special rule. Go to Design, Rules, and tell in this rule that if the net is ground and if it's connecting to a path, then use thermal relief of this style. These numbers here, you may want to calculate them. It really depends how high current will flow through these pins. So sometimes keep these tracks which are here white if it's power. In this case it's power because it's ground. And I will call it, for example, I'm gonna do path. Now watch what will happen. All the ground through-hole pins will use this thermal relief, and all the other vias and pins will use the direct connection. See? Here is a ground pin and it uses this thermal connection. Here are the ground vias, they are still using the direct connection. Here are also ground pins, see? Sometimes these power planes, they do not refresh automatically in Altium. So you may want to, for example, click and then it's fine. See, here I don't see the thermal relief. When I click, it's now there. See? They probably will fix it in next version. I just wanted to show you that sometimes it may look like the new rule will do nothing, but you may need to refresh the planes or polygons. Don't forget to refresh them. 2 useful tips. When you are drawing polygons, always be aware where you draw the edge of the polygon. What do you think? What is better? If I draw the edge here or here? Between these vias or through the vias? Think about it. I will put it here. Between the vias. Watch what will happen. We'll refresh the polygon. Can you see it here? Basically, if you draw edge of the polygon between vias, you actually lose this space, which otherwise could be used for copper. And sometimes it's very important that some planes, they are high currents and you really would like to use this space for copper. If you draw this edge through the vias, and when I refresh it here, see, I can use this space between the vias for copper. It's really small trick. It may look like it's not important, but yeah, sometimes it really is important. It will help you increase the copper width for the high current planes. This is the second tip. Have a look on this situation. Here we have some power vias in this area here, but we used a huge power plane around them. We don't have to use so big power plane. We could just draw a smaller power plane. But if I'm drawing a high current power plane, and if neighbor layer is ground layer, and if there is a lot of free space on this power layer, then I will always try to make the high current power plane as big as possible. It's because you remember when we were speaking about layer ordering, I mentioned that if you have a ground plane and you have a power plane, then together they can create some kind of capacitor which can help you filter noise on the power plane. This is the case. And bigger the area when these ground and power plane are together, better filtering. So always in my designs, when I have high current power plane and there is some free space on this layer, I try to make it as big as possible. But it has to be, neighbor layer has to be the ground plane, and these planes need to be inside the PCB. I do not draw huge polygons or huge planes on top or bottom layer. Okay, we have the polygons. Now we can improve them. What can we improve? We can improve the amount of copper flowing between vias on these power layers. What do you think? Why we can improve it and how we can improve it? I'm going to show you. Have a look how small holes are on the power plane layers. See? Here the hole is only the hole size, so 0.2 millimeter, plus the standard clearance, which is 0.1 millimeter here and 0.1 millimeter here. So when I measure it, then the hole here is 0.4 millimeter. But here there is something different. What is different? Here is this copper around this hole. So hole in this polygon is much bigger than in this power plane. See? Because the size will be the hole size plus the via plus the clearance. When I measure it, then it is 0.663 millimeters. The thing is, this copper which is here on this power layer will be removed. During manufacturing, this copper will not be here. It's because these vias are not used on this layer. So this ring doesn't have to be on this layer. And it means we can safely make these holes smaller on these layers where we have these polygon planes. How we can do it? We can set a special rule. So have a look. First I'm going to measure this, so you see what is the distance between this and, okay, I will use this one. I will use this. See what is clearance. 0.1 millimeter is the clearance between this via and this polygon. We are going to make it smaller. Go to Design, Rules, Clearance, and we will create a new rule. This one. Here. This is the rule. And we would like to use 0.075. So on these layers where we have the polygons, and in the situation there is polygon and via, we would like to have clearance not 0.1 millimeter but smaller, 0.075. Let's do it. I will cancel this. Don't forget, we need to redraw the polygons. So rebuild all. This is not only improvement. I will show you some other improvements too. Okay, now let's measure it. Between this via and this polygon, the clearance is 0.075. See? And now the copper is wider. Theoretically, you could make it even smaller, these holes, but we had some feedback from production. They didn't like it, so I don't do this clearance smaller than the smallest clearance which is possible to be done by the PCB manufacturer. Theoretically, you should be able actually make this hole which is here almost exactly same as this hole, because that's what is on this layer. Yeah. If you need to make it smaller, you can try, but check with your PCB manufacturer first. Another improvement. When you are drawing polygons, always try to keep bigger gap between power polygons than it is the standard minimum gap which you use. For example, we normally use minimum clearance between polygons to be 0.2 millimeter. And we also normally draw the polygons the way that there is 0.2 millimeter. You can very easily set up the snap grid to be 0.1 millimeter, and then you can draw it very nicely with the gap 0.2. If you would like to be sure that all the polygons are routed the way that the gap is at least 0.2 millimeter, you can create a rule, and in the case the gap is smaller, it will increase it. I made this polygon here a little bit bigger, so I made this gap smaller. When I measure it, gap between these polygons is 0.102, so it's less than 0.2. And I'm going to show you how you can set up the rule which will make this small gap between these polygons a little bit bigger. Go to Design, Rules, again Clearance, New Rule. I always look which one was added as the latest rule. It's this one with priority 1. So I double click here, and now we need to create a rule polygon to polygon. We would like to apply this on the layers L5, 6, 7 and 8, and this rule will apply between the polygons. Instead of 0.1 millimeter, we would like to have 0.2 millimeter. Okay. Now, if in your design you have on these layers gaps smaller than 0.1, based on this rule, when we rebuild these polygons, it will get wider, you will see. But normally I try to draw them the way they are, the edges of the polygons are at least 0.2 millimeter. See, now it is wider. Based on the rule, it is now wider. Very similar way, we can improve also the polygons on layer 2 and layer 11. These are the layers with the short connections between microvias. And you can see in busy areas, this copper is very small. What can we do? Instead of using default 0.1 millimeter, we can use something smaller. I will measure it, so you can see what is the current clearance, 0.1. And for example, again, we don't use maybe the smallest clearance, but we still can use something smaller than 0.1. For example, 0.085. Let's set up a special rule. Go to Design, Rules, Clearance, right-click, New Rule, and we will call it Polygon Clearance on layer 2 and layer 11 for everything. Here is the rule, and we will change it to 0.085. Okay, watch this. We will make it bigger. See, right click, rebuild all polygons, and then I measure what is the distance. Before it was 0.1, now it will be, see, it is wider. Now it will be 0.085. And again, as before, we can improve it again. We can improve the smaller gap even in the areas where are the through-hole vias used, because these through-hole vias, this copper around through-hole via will be removed during the PCB production. So we can safely change this gap, which is now here 0.085. We can safely change it to 0.075 as on these other layers which are here. So let's create one more rule. Go to Design, Rules, Clearance, New Rule, double click, and it will be like this. On the layer 2 and layer 11, if it's polygon and if it's a via with a hole size different from 0.1, because 0.1 is the hole size for the micro vias. So for all the through hole vias, we would like to apply 0.075 clearance. Okay. Now watch. Rebuild polygons. Why we are doing this? Because you always would like to have the power planes and ground planes as good as it is possible. And sometimes if you don't change these rules, then you will see if you need to use bigger minimum clearance, you will get really bad planes. So in these cases, it is really needed to set these special rules for the polygons. So let's measure it between through hole via and polygon 0.075, but between this via, micro via and polygon, it is still 0.085. Perfect. Don't forget, it is very important, you need to watch the priorities in the rules. Design rules. And when you click on the clearance, here are the priorities. And the priority of these rules need to look like here. Otherwise, you may not get the results which you would like to have. So for example, otherwise you may have 0.075 around everything instead of having 0.075 only around the through hole vias. Don't forget, watch these priorities which are here. If you need to change priority, you can do it here. Decrease, increase, you can move it. Before we finish, couple of tips. If in your design you have some polygons where very high currents will flow through, then you can, for example, increase the copper thickness, we were speaking about it, or you can use multiple layers for the polygon. For example, you can go and copy and paste this polygon also on other layers. Select the polygon, Ctrl C, go on layer 2. This is an example. I deleted the ground from this layer because I would like to show you how to copy and paste polygon on different layer. Go to Edit, Paste Special, paste on current layer, keep net name, paste. Okay, now we have this polygon on layer 1 and we have exactly same polygon on layer 2. If I double click here, you see the net name is +1 V375. On this layer 2, this new polygon, it's called +1 V375. Exactly same name. Some people ask me if in my designs I fill up this unused space on the top and on the bottom layer, if I fill up this space with a ground planes. No, I don't fill them up with ground. In most of the PCBs what I design, the second layer from the top and the second layer from the bottom are full solid ground planes. So it's not necessary to also place ground planes on the top and bottom layer. And another reason why I don't do that is because I read some articles, I read some books, and they tell you that if you use these huge ground planes on the top and on the bottom layer, you need to know how to connect them. They need to be connected properly. If they are not connected properly, they can make EMC results of your PCB worse. So normally in my designs, I use the second layer from the top and second layer from the bottom solid ground planes, and I do not place any big ground planes on top and bottom layer. No problems. Okay, sometimes I do use ground planes on the top or on the bottom layer, but it is only because it is required for some reason. For example, this ground plane can be sometimes used as a heatsink. In this case, in the case when I use ground plane on the top or on the bottom layer, I always place there a lot of ground wires, so I'm pretty sure the connection of this ground plane is a really good one. And the final tip, when in the phase 2 you are replacing tracks, power tracks, by polygons, you don't have to delete these tracks one by one like this. Delete, delete, delete. Yeah, you can use a simple filter to simply delete these tracks. Here is the filter. If it's track on the power layer 7, this is the layer, and the net name is this one. When I click here, this is the net name. Then select this track and apply to all. Now press delete, delete the track. Now I can highlight it and you can go to place and draw the polygon. Okay, I'm sure you understand. You don't have to draw it. When we were speaking, do you remember when we were speaking about vias disappearing when you connect, when you draw a track and try to connect the vias which are connected also on other layer together, like this. Here they are connected on the top layer, and if I try to connect them also on this layer, then the via will disappear. Do you remember it? Do you remember also what I recommended? I recommended you to always connect only one via. There is also second option what you can use, or what will help you in this situation of magic via disappearing. You can lock down these vias. So if I lock down this via, I need to clear filter. If I lock down this via here, and if I draw the track now, the via will not disappear. See? So in case you have a bunch of vias connected in one net, then you have two options. You can connect only one of the vias, or you can lock down all the vias and then they will not disappear. I only wanted to mention it because I think it's really useful, and we sometimes use it, and I forgot to mention it in the previous lesson. And that's all for this lesson. When you are done with the polygons and with power planes, your PCB is basically finished. Next week we are going to speak about fine-tuning. So we will go back to the nets which need to be length matched, and we may need to add a little bit of track, or we may need to remove a little bit of track to exactly meet the design guide requirements. We will also speak about how you can check your PCB, and also about what kind of other information you may want to include in the PCB. For example, information for PCB manufacturer. You will see. Don't forget, go on the lesson web page, read the activities, and practice. Practicing is much better than just watching a video. When you practice, you will remember it better and you will learn more. Again, it's for you. And I will be very happy if you keep working on your own PCB, and this week you improve the layout of your PCB and you add the polygons and planes, power planes. I hope you like this lesson, and I'm looking forward to speak to you also next week. See you.